Okay, so looking in this study part, what we're here to look at for the first part is just the beginning section of this booklet, the section on electronegativity and bond polarity. And one of the key definitions from year 12 is to understand what we mean by the term electronegativity. And you need to be able to define that. What we've got to then do is use this idea about electronegativity to explain why some bonds are polar. Now, those of you doing biology may have some understanding of what we mean by polar already. What does that mean, polar? Okay, an uneven distribution of charge. So you're thinking about one end being perhaps slightly positive and one end being slightly negative. When we think about the Earth, we think about the Earth being polar. It's got a North Pole and a South Pole. The North Pole is different to the South Pole in terms of what our magnet, our compass, would interact with it. So there is some difference. And when in chemistry and biology, when we're thinking about electronegativity and polar bonds, we're thinking about one end being slightly positive and one end being slightly negative. And we need to think about why that can happen. Okay, so first of all then, electronegativity. What is it? We've got to be able to define this. It says underneath in the space where we're going to write the definition, some elements have a greater pulling power and are more effective in attracting pairs of electrons. We're going to use an analogy to think about this. You think about you and the person sitting next to you, and you've got a bag of sweets, and you're both holding on to the bag of sweets. You both want the bag of sweets. Now, if you've both got the same pulling power on the bag of sweets, where does the bag of sweets end up? Where does it go? It stays in the middle. You're both pulling on the bag of sweets. It's not such a terribly packaged one that it rips open. You're both pulling on the bag of sweets. It stays in the middle. Now imagine one of you has more pulling power. The bag of sweets moves closer to the person with the greatest pulling power. That's an analogy, but this is basically what electronegativity is. It's about pulling power. We're not talking about bags of sweets. We're talking about bond pairs of electrons. Yes. So we can use this idea to understand why, for example, a bond pair in H2O is pulled close to the oxygen. The oxygen must have greater pulling power on the pair of electrons compared to the hydrogen. Now, clearly, in an exam situation, we can't write about pulling power. It doesn't sound very, very technical, does it? This element's got more pulling power. But what we can talk about is this element is more electronegative than that, and so the consequence is this. Okay? Okay, so electronegativity is the ability of an atom to pull a bond pair of electrons, a covalent bond, towards itself. And there are going to be clearly factors that are going to affect the electronegativity of an atom. So what I need you to do with the person sitting next to you on your whiteboard, jot down what might affect. If watching this video at home, you can do it at home as well. What might affect the electronegativity of an element? How does electronegativity change as you go across the period? If you're doing this at home, pause the video and have a think, and then you can rejoin in a moment. Okay, so hopefully you have thought and come up with some ideas about why and how electronegativity might change across a period. What I want you to do, rather than just immediately talking about that, however, because I can see that some of you have come up with some great ideas already. The most obvious one What's the most obvious thing that changes as you go across a period? Number of protons, the atomic number. There's an increase in the number of protons. There's an increase in the nuclear charge as you go across a period. It's becoming more positive, that nucleus. So you think about the ability of that nucleus to pull a pair of bond electrons towards itself. If the nucleus has got more protons in it, will it be more or less able to pull a bond pair towards itself? More. Okay? So have a think about that. Do you need to talk about anything else in your answer? Because clearly the next question is going to be this one. How does electronegativity of an element change down a group? So again, on your whiteboards, think about, do you need to say anything else for that first answer about how it changes across a period? And now what do you need to say for how does electronegativity of an element change down a group? With reasons. Again, I'll pause the video so you can have a go at this if you're watching at home. Okay, so let's think about how and why, when we're ready, all these things are changing. Imad, how does electronegativity change across a period? Does it increase or decrease? What does that mean? Is it more or less able to pull a bond pair towards itself? It's more able. Atoms are more able to pull bond pairs of electrons towards themselves as you go across a period. Why might that be, Damilola? Okay, so there's an increase in protons in the nucleus. Right, okay, let's think about going down the group. How does electronegativity change as you go down a group? Samaria? Decreases. Is there an increase in nuclear charge as you go down a group? Yes. So we can't just use the idea of increasing the number of protons or increasing the number of in the nuclear charge, because nuclear charge and number of protons increases as you go across a period, and it increases as you go down a group. Yet we've got different things happening to electronegativity. So what else is it that we've got to talk about? Shielding and atomic radius. How does atomic radius change across a period? Okay, atomic radius decreases. Why do atoms get smaller as you go across a period? Okay, we know there's an increase in protons, but what else do we need to consider? It's great to pull on the nucleus and outermost. Where are those outermost electrons? Okay. Electrons are in the same shell. So what else stays the same? No difference in shielding. Now, this looks like good value to me. We've got a new concept to learn, and the things that we're using to explain this concept, we've come across before. What was the concept that we've come across before that changed across a period, and we explained it in terms of putting more protons in the nucleus, but the electrons were going into the same shell, and there was no difference in shielding? Ionization energy. Ionization energy does what as you go across a period? Increases. It becomes harder to pull electrons off because they are more tightly held. Well, we're looking at this from a slightly different perspective. Electrons are more tightly held as you go across a period. It becomes harder to pull them off for these reasons. Electrons are more tightly held. They're more pulled in, including bond pairs of electrons, for exactly the same reasons. What else changes as you go across a period? Well, it's already displayed, isn't it? Atomic radius decreases for the reasons that we've got written down. Now, if the argument is the same for ionization energy across a period, the argument will be the same as ionization energy down a group. It becomes easier to pull electrons off atoms down groups. Electronegativity decreases down a group. Electrons are less tightly held. They're less pulled into the nucleus because down a group, atomic radius increases. Outermost electrons are in shells further away from the nucleus, and there is more shielding. Okay, so we've got the reasons written down for why electronegativity increases across a period. In the space you've got in your study pack, can you write down what are the reasons for electronegativity decreasing down a group? So using the reasons we've just talked about, fill in why does and how does the electronegativity of an element change across a period? And then, how does electronegativity of an element change down a group? Fill those two bits in. Okay, so looking at how electronegativity decreases down a group, it gets less. Why? How are we going to phrase this? Imad? Give me a reason. Why does electronegativity decrease down a group? Okay, yeah, we know nuclear charge is increasing, but I think it's a lovely word that a number of you have used about it being negated. There are other factors which are more important. What are those other factors? Shielding is it? Why is shielding increasing as you go down a group? Because we've got more shells. Okay, so the first thing is the outermost electrons and I think we need to get onto this at some point, including the bonding electrons, because really that's what we're talking about. We're not just talking about any old outermost electron, we're interested in the bond pair. So the bonding electrons are in a shell further from nucleus. That's the first point. There's more shielding. What's the last thing we need to say? It's the same argument that we had for ionization energy. What's the last thing we talk about going down a group? Outermost electrons are further from the nucleus. There's more shielding. So what? So less attraction. Between the nucleus and what? What is it that I'm interested in? And the bond pair. Okay, when you have got that written down, consider this. Look at your periodic table, identify which element must be the most electronegative. Why do we not need to think about electronegativity of the group 0 elements, the noble gases? And then briefly, what are the three factors that we have talked about that might affect electronegativity? So have a think about those, jot them down, and then we'll check in a moment. Okay, so we've talked about the idea that electronegativity increases as you go across a period from left to right. We've talked about the idea that electronegativity decreases down a group. So the most electronegative elements are going to be at the top of their group. But we know that it's increasing as you go across a period. So if you look at a periodic table, that eventually is going to bring you all the way over to fluorine. Fluorine is the most electronegative element. It's the one which is furthest across the period to the right-hand side, and it's the one which is at the top of the group. Why are we going to not think about electronegativity of group 0 elements? What do group 0 elements not do? They don't bond, okay? If they don't bond, they're not going to have electrons as covalent bond pairs. So they can't pull a bond pair towards themselves if they don't bond. So that's why we're going to ignore group 0. So which is the least electronegative? It's not cesium. Looking at the periodic table, which is the least electronegative element? Francium. It's the one that's at the bottom of group 1. Francium. All right, well, never mind. What are the factors which affect electronegativity? Go there, name one, please. Nuclear charge or number of protons in nucleus? Is there another one, please? Shielding. Last one. Distance between nucleus and the bond pair. Okay, so it's like linked to atomic radius, isn't it? It's linked to where the electrons are, the number of shells. So what we're really, the main point of all of this is, how does the difference in electronegativity affect the bond between two atoms? A little bit of space repetition. Draw me, please, a dot and cross diagram for a chlorine molecule. And think about what type of bond you have got. So we've got our dot and cross diagram of our chlorine molecule. Clearly, we've got a covalent bond between the two chlorine atoms. Why is it a covalent bond? Lovely. The pair of electrons is shared in the space between two chlorine atoms. Where exactly is that pair of electrons being shared? Where? Whereabouts? In the middle. Exactly in the middle. It's exactly in the space between the two atoms, in the middle. That's important. Jesse, that does mean that we can draw our chlorine bond with a line. The line's representing the covalent bond, okay? And you'll have done that at GCSE. We can draw dot and cross diagrams, or we could just draw our molecule as two chlorines with a line between them. What's the line representing? A single covalent bond. How many electrons are on that line? A pair. It's a covalent bond pair. Okay, same process. Can you draw me a dot and cross diagram for a hydrogen fluoride molecule, and then try and think about which atom is more electronegative than the other one, and then where will the bond pair of electrons be pulled towards? Have a think about that. We'll come back in a moment. Okay, so looking at this, Damilola, which is the most the more electronegative out of hydrogen or fluorine? Fluorine, okay? The fluorine atom is more electronegative than the hydrogen atom. And because one of these atoms is more electronegative than the other, the shared pair of electrons is not shared evenly in that space. It's going to be pulled towards F. So that means that there is going to be a build-up of electrons on the F, on the fluorine side of the molecule. Electrons, the bond pair, is being pulled towards the fluorine. So there's going to be a build-up of electrons on the fluorine side, and there's going to be a decrease of electrons on the hydrogen side. So the bond becomes polar. Okay, the bond is becoming polar. One end is becoming slightly positive because it's losing electrons, and the other is becoming slightly negative. It's gaining the electrons. Now, this is the important thing. If we've drawn our hydrogen fluoride, we clearly still need to draw the fact that we've got the covalent bond between the two atoms. But what we've just said is fluorine is more electronegative than hydrogen. So fluorine is going to pull that bond pair of electrons towards itself. And that's going to make the fluorine end of the molecule slightly negative. How do we show this? I need to use a special symbol. I need to use slightly negative and slightly positive. Delta negative, delta positive. This letter that we're now introducing you to, if you're not an expert in Greek, this is the lowercase Greek letter delta. Okay? It is not the capital Greek letter delta. That comes in later in the course. That's a special treat for another day. It means, an easy way to think about it is it means slightly positive, slightly negative. So some people, although it is the Greek letter delta, some people struggle to draw this. Well, one way to draw it is to kind of do a bit of an S and then link it back. S for slightly positive, slightly negative, even though it is a D, a delta. Now, in these very, very important statements, the greater the difference between the electronegativity of the two atoms, the more polar the bond will be. There's no real way that I can draw that. That is something that you've just got to know just by looking at the atoms concerned. So if I put in more electronegative elements, I have a bigger difference in electronegativity between the two atoms. It will become a more polar bond. But I can't do anything other than use delta positive, delta negative to show that. Can electronegativity be used to predict the types of chemical bond? Yes, obviously, it's telling us that. That's what the interesting thing is that we're going to look at. Now, here is the thing. This is the A-level stuff. If we think about a pure covalent bond, so far we've thought, for example, about a chlorine molecule. The bond pair is shared equally because each atom has the same electronegativity. The bond pair is exactly in the space between the two atoms. It's exactly in the middle. If I get a small difference in electronegativity between two atoms, for example, hydrogen and fluorine, I've got a difference in electronegativity, I'm going to get a polar covalent bond. The bond pair is being shared unevenly. It is being pulled towards the more electronegative atom, making that end of the bond more negative. So what's ionic bonding then? The difference in electronegativity between the two atoms is so great that one of the atoms doesn't just pull the bond pair a little bit towards itself, it pulls it entirely off and onto itself, so that one of the atoms doesn't have any of the bond pair, whereas the other atom has entirely got the bond pair. And you end up with oppositely charged ions. So it's almost as if in sodium chloride, you think we could try and draw a covalent bond. We know that that's not the case. That doesn't happen. But if we try to draw a covalent bond, the difference in electronegativity between sodium and chlorine is so great that the bond pair is entirely pulled off and away from the sodium and moves entirely onto the chlorine to make the chloride ion. The bond pair are stuck entirely to the chlorine, making a chloride ion. There's no sharing of that bond pair. So really, bonding is a bit of a continuum. How do atoms know whether to do ionic or covalent bonding? At GCSE, you would say, oh, because they're either metals or non-metals. The atoms don't know whether they are metals or non-metals. They have no idea. They're not alive. They have no sense. You know, they don't. So how do we decide what happens? Really, it's to do with the difference in electronegativity. We know that things on the right-hand side of the periodic table have a low electronegativity, whereas things on the right-hand side of the periodic table have a high electronegativity. And because that difference in electronegativity is so great, the more electronegative atom pulls the bond pair entirely off the metal and onto itself. Much more subtle understanding of what bonding is, which means that there are examples of compounds that contain metals and non-metals where the difference in electronegativity is small, which are covalently bonded.